Okay, now let's see how we can use L'Hopital's rule if we're dealing with something besides a quotient of functions, maybe a product, a sum, or differences. L'Hopital's rule as it applies to products, sums, and differences. Okay, so if you recall, the standard L'Hopital's rule applies to a ratio or quotient of two functions whose limit results in an indeterminate form. We still, whether we have a product, sum, or difference, we still have to have an indeterminate form in order to use L'Hopital's. And the goal is going to be to convert the product, sum, or difference into a quotient to apply L'Hopital's rule as we know it. So let's begin with an example. And let's determine the limit as x goes to infinity of x times e to the negative x. And so in this case, as x goes to infinity, we end up with infinity, right? X goes to infinity. So this guy approaches infinity times e to the negative infinity is 0. So this thing's approaching infinity times 0. One part of it's getting really big times the other part's getting really tiny. Again, we have this battle. These two guys are at odds. One part of the product's growing while the other part's shrinking. So does the infinity win out and turn this product into infinity? Or does the 0 win out because it's shrinking faster than the infinity is growing? And we get 0. Or do they meet in the middle and end up with a finite number? This is indeterminate. But this is not a quotient of functions, so I can't use L'Hopital's just yet. So what I need to do is rewrite this product as a quotient. And this one is pretty straightforward. This is the limit as x goes to infinity of, well, e to the negative x literally means divide by e to the positive x. So this is the same thing as x divided by e to the positive x power, okay? And upon examination here, we now have a quotient. Is this still indeterminate? It has to be indeterminate at this point in order to use L'Hopital's. Well, if we do direct substitution, we get infinity on top. E to the positive infinity now is also positive infinity. And yes, we do get an indeterminate quotient. So now we can use L'Hopital's to finish this problem. Taking the derivative of the top, I get 1. And taking the derivative of the bottom, I get e to the x. And now, I know that I won't get an indeterminate form because my numerator is 1, a constant, a finite number that's not 0. So I'm going to get 1 over e to the x as x goes to infinity is, let's not write 1 over infinity. Okay, that's bad practice maybe. We get 1 divided by infinity, and 1 divided by a massive number is 0. Okay, approaches 0. So this limit is 0. So in fact, in this indeterminate product, the 0 wins out over the infinity. The 0 is shrinking faster than the infinity is growing. Okay? So that's an interesting example. Turn the product into a quotient. Let's see another one. Let's determine the limit as x goes to 0 from the right of x times the natural log of x. And so one thing maybe we haven't mentioned so far is that your limit can be a one-sided limit and you could still use L'Hopital's, okay? So it's sort of universal amongst all limits. The key is that the function you have here is indeterminate and you can differentiate the pieces to use L'Hopital's rule. So if we look at direct substitution in this case, 0 goes in for x, we get 0. It's a positive small number. We might want to remember that. But the reason we're approaching from the right of 0 is because of this natural log. We can't approach x from the negative side because you can't take natural logs of negative numbers. So as x approaches 0 from the right of the natural log function, the natural log of really tiny numbers, if you remember the graph, goes down to negative infinity. So this turns into 0 times negative infinity, which again is indeterminate because we've got a small times a big. Who wins out? So let's see if we can write this as a quotient in hopes that we'll get an indeterminate form there, allowing us to use L'Hopital's rule. So we're not using L'Hopital's yet. I need to rewrite this as a quotient first. Now, I need to take one of these factors in this product and move it to the denominator. The easiest way to do that, this natural log of x is the more complex factor here. So I'm going to leave him in the numerator of this invisible fraction that I have here. And I'm going to move my x to the bottom by changing it to its reciprocal, okay, which is 1 over x. So you can take any piece of a product and move it to the bottom as long as you flip it over, right? Multiplying by something is the same thing as dividing by its reciprocal. Say that again. Multiplying by x is the same thing as dividing by the reciprocal of x, 1 over x, okay? Now, we hope that this is indeterminate as a ratio so that we can apply L'Hopital's. We already know that as x approaches 0 from the right, the numerator goes to negative infinity. As x approaches 0 from the right on the bottom, I get 1 divided by a number that's positive but shrinking. So I'm going to get a positive ratio. And when I take a constant number divided by a shrinking small positive number, I get positive infinity, which luckily for us is indeterminate because now we can use L'Hopital's. I'm not spending a lot of time on the derivative parts of these problems. You know all your derivative rules. The derivative of natural log of x is 1 over x. The derivative of 1 over x, well, that's x to the negative first power. You could use the power rule. And if you do, you get negative 1 over x squared, okay? And if we simplify the complex fraction, looks like we're going to get negative x, okay? Very simple, negative x. And as x goes to 0 from the right of negative x, we can actually evaluate that limit. Just plug 0 in for x, and we get 0. All right? So here we had, it wasn't quite as obvious how to turn this into a quotient, so we learned that we can, if we've got multiplication, we can change it to division by the reciprocal. And in this case, we didn't want to do the reciprocal of the natural log function. Instead, it's much easier to do the reciprocal of x on the bottom. Okay, let's move on to the rest of the video, which deals with sums and differences. When you're dealing with the sum or difference, you still need to have an indeterminate form to start with. Then you have to turn your function into a quotient so you can apply L'Hopital's, okay? So here we go. Let's consider this example. Determine the limit as x approaches 0 from the right of 1 over x minus 1 over sine x. And of course, 1 over sine x is cosecant of x. It could have been written that way as well. So we need to investigate this limit. And so you always start by trying direct substitution. If we take 1 divided by a number really close to 0 from the positive side, then we get positive infinity. Minus, if we take the sine of something really close to 0 from the positive side, we get something close to 0 from the positive side also, right? The sign of a positive number is positive, the sign of 0 is 0, so this gives us a 0 that's positive. And 1 divided by a number really close to 0 from the positive side is still infinity. So we end up with this infinity minus infinity. So we have this fraction's approaching infinity, this fraction's approaching infinity, and we're subtracting. Now the first fraction and the second fraction approach infinity at different rates. One is going to get there quicker than the other. The question is, who wins? Which infinity dominates this subtraction? We don't know. This is indeterminate. It has to be. If we had infinity plus infinity, they're working towards the same cause, right? A massive number plus another massive number gives us a massive number. If I have one massive number minus another massive number, one of those is going to win, or they're going to be about the same. They're both going to approach infinity about the same rate, so that when we subtract, we get a finite number. So we have to investigate this further. So what we need to do to use L'Hopital's is put the two fractions together with a common denominator. So that's going to give us a single fraction, allowing us to apply L'Hopital's rule. So I'll multiply my first fraction on the top and the bottom by the sine of x, and my second fraction on the top and bottom by x. And so this gives me the limit as x approaches 0 from the right of sine x minus x on top over x sine x, which is my common denominator. And now at least I have a ratio of two functions. So I could check them out by direct substitution and see what we get. So plugging in 0 for x, I get sine of 0 is 0, minus 0 is 0. On bottom, I get 0 times the sine of 0. 0 times 0 is still 0. We're indeterminate as a ratio. Now we can apply L'Hopital's directly. So I'll keep my limit, and I'll differentiate my numerator and my denominator separately. So on top I have a difference. The derivative of sine x is cosine x, minus the derivative of x is 1. On the bottom I have a product. I have to use the product rule. So I'll take the first function, x, times the derivative of sine, which is cosine x, plus the derivative of x, which is 1, times sine x. And I'll reevaluate my limit now. As x goes to 0, cosine of x goes to 1. So I have 1 minus 1, which is 0, over 0 times 1 is 0, plus the sine of 0 is 0. So 0 plus 0 is also 0. We still have an indeterminate form. Let's apply L'Hopital's again. So on the top, the derivative of cosine of x is negative sine x, minus the derivative of 1 is just 0. On the bottom, I have to use the product rule again for this first part of the sum. So I'll take the first function times the derivative of cosine x, so x times negative sine x gives me negative x sine x, plus the derivative of x is 1 times cosine x. Plus the derivative of sine is another cosine x. So product rule gave me these two terms, plus the derivative of sine gave us this cosine x. Direct substitution again. On the top I get the sine of 0 is 0, times a negative is 0. On the bottom I get 0 times the sine of 0, that's 0, plus cosine of 0 is 1. So I've got 0 plus 1 is 1, plus cosine of 0 is 1 again. So 0 plus 1 is 2. It's not indeterminate anymore. 0 divided by 2 is simply 0. So this limit, after getting a common denominator and two applications of L'Hopital's rule, we see is 0.